Hi everybody. Today I'm going to talk to you guys about something called a free body diagram. Free body diagrams are kind of a weird name, but really what you want to think about is that they're actually ways to represent the forces that are acting on an object so that we can do a better job of analyzing if there's a net force. And then of course, if there is a net force, we should use Newton's second law to be able to calculate the amount of acceleration that the object experiences. And so we need to make our lives a little bit easier to be able to do that, and we can do that through something called a free body diagram. Now, people get confused by this idea of a free body. Oftentimes they'll call it a force diagram, but really what you have to remember is that a free body really is any object that, if there's a net force, it can accelerate. So it's free to move or change its motion based off of the forces that are acting on it. That's not necessarily to say that it will always move if there's a change in the force. For example, if you get into your car, the road supports the additional weight of you and the car together. And so the additional force that the car experiences doesn't actually change its motion because it's balanced out by the road. But it could move if you dug a hole and then drove the car into a hole or something like that. Anyway, so we're going to talk about cars today, and so the first situation is a car that is moving to the left, and it's moving at a constant velocity. So you have to remember back to the first unit what a constant velocity actually means. So every time you see that, constant motion, constant velocity, you should remember that there's no net force acting on the object. We would say it's in equilibrium, and its motion is dominated by inertia, not by the forces that are acting on it. So keep that in mind. If there's zero net force, then what we should find is that all the forces are going to balance out. And so as we go through here, you'll see they will balance out for this first situation. So again, a car is moving to the left at constant motion along a perfectly horizontal road. The horizontal road part we'll talk about in just a minute. If you want to depict a force, there's some things that you really want to think about. And I have an acronym that's CODS, C-O-D-S, and that I came up with, and here's what it stands for. C stands for the cause of the force, and you usually find the cause of the force in the label itself. So F sub G would be the force of gravity. What's the cause? It's the gravitation. The next letter in there is the object, so O, object, and so that's what it actually acts on. And you're going to see that the tail of the force that we draw as an arrow is going to sit on the object that it's acting on. This is a little different than what you might see in an engineering class, so just keep that in mind if you've been through engineering. The direction of the force, the action of the force, is in the direction that the arrow points, and the size is actually the length of the arrow. So together we've got CODS, cause, object, direction, and size. Those are the four most important things when you think about what forces are doing to an object. Now, we don't often draw it like this, but you should consider the size of the arrow as being representative of the size of the force. So for example, for situation number one, a car has a pretty large weight, and so we're going to draw that as a long arrow. And of course it's pointing towards the center of the earth, so that's what I drew there in that first scenario. Now it's not falling, so we know that the weight force, the gravitational force, is being canceled out by the force of the road, which we call a normal force. And the fact that the road is horizontal means the normal force perfectly cancels out the weight of the object. So it won't begin to roll by itself because it's on a slope. So the verticals cancel out. Now, it's moving down the road at a constant velocity, so we know there must be horizontal forces that are acting on it. And the big one there, of course, is that little f, friction and air resistance or drag. And so that's happening. So what's happening, what the person who's driving should be doing is applying a force with the engine. And what we find is that the engine force and the friction and drag forces all cancel out. One going to the left, the engine force, and one going to the right, the friction and drag forces. Now, if you see all forces cancel out, you should understand that there's no net force, which means there's no change in motion. Situation 2 is different because the car is braking when it's moving to the left. And so braking implies a changing motion, which means there must be a net force. And so the question is, where does that net force going to go? Well, we shouldn't expect to see it vertically because it's not changing its motion in the vertical direction. It's only changing its motion in the horizontal. And so as a result, we should see that maybe the verticals cancel out, but the horizontals do not. And that's exactly what we find. So here I've drawn the verticals there, just like we did before, the gravitational force going down and the normal force going up, and they are the same size. I've drawn them to be the same size, and they are perfectly opposed, so they cancel out. So it's not a vertical force there, it is a horizontal one that's going to have the net force. Now if it's moving to the left, the brakes are applying a force to the right. So they're slowing it down, right? There's also there's also friction acting and air resistance, and so that is also moving to the right. And so you have two forces that are pushing the car to the right, which means there is a net force, and that is to the right, and it's the addition of the brake force and the friction force, and you can easily see that from the diagram. The horizontals do not cancel out, and so if we added those two forces together, we'd be able to come up with the net force. And the net force then could be plugged into F equals ma, and we could go ahead, if we knew the mass of the car and the sizes of the forces that are acting to the right, we could add those two together and then divide by the mass to figure out what the acceleration is that's being applied to the car. So we could find out really what the rate of its slowing down was using Newton's second law. So free body diagrams are super handy, they're super helpful, they are very useful, but they have to be done correctly. So don't forget the cause, object, direction, and size acronym, and then also don't forget to try to draw them roughly to scale. There will be times when you actually have to draw them to scale, but for us for right now, just draw them roughly to scale, it should be good. We typically do thumbnail free body diagrams, which you don't have to be as accurate about. But you can see that I drew the braking force and the friction force to be much smaller than the gravitational force or the normal force acting on the car in the second situation there. And I did that for a very good reason, because they are smaller. Hopefully that helps. We're going to be using this again tomorrow and in the days to come, so please make sure that you have a pretty good understanding of at least the basics of it so that we can practice it coming up. Thanks.